point we've learned how to add, subtract, and multiply polynomial expressions. What we want to, and then also factor polynomial expressions. What we want to do now is apply the idea of factoring a polynomial function to, or polynomial expression to the reality of solving a polynomial function. The way we're going to phrase this, though, is called zeros of a polynomial. We're going to talk about this in the context of what it says right up here. The zeros of a polynomial function f of x are the values of x that make the equation equal to 0. So, in our example, it says here, if f of x equals x to the third minus x squared minus 6x, then the zeros of f of x are the solutions of the equation 0 equals x to the third minus x squared minus 6x. So notice what I did. I plugged 0 in for f of x because it says that the zeros of a polynomial function are the values of x that make the equation equal to 0. So I'm setting my equation equal to 0, and now I need to solve for x. I need to find the values of x that make my equation here equal 0. Okay. So let me recopy that down right here. 0 equals x to the third minus x squared minus 6x. So the challenge now is to figure out how to find the values of x that make this equal to 0. When dealing with polynomials, the best way to do this, and really one of the only ways to do this, is to factor the polynomial. So let's go ahead and factor this polynomial. First thing you always want to ask yourself when factoring a polynomial is, what is the greatest common factor of each term? Now, looking at these three terms here, I see that they don't all share a coefficient. Well, they all share a coefficient of 1, but that's not significant. But they do all share one multiple of x. So I am going to factor an x out of each term. Factoring an x out of x to the third produces x squared. Factoring an x out of negative x squared produces negative x. Factoring an x out of negative 6x produces negative 6. So we successfully factored out the greatest common factor of that term, or of each term. Notice that what we have left in the parentheses is a quadratic. We know how to further factor quadratics. The coefficient in front of x squared is 1, so I'm going to use 1 and 1 to multiply to 1. And then I've got my constant down here of negative 6. I'm going to choose negative 3 and positive 2 as the two factors of 6 or negative 6 that multiply to negative 6. Multiplying straight across, we get negative 3 and 2. These add to negative 1, which is the coefficient in front of our x. So these two sets of multiples satisfy that specific condition. So we can pair up diagonals of the two sets of factors that we chose for the first coefficient and the constant. And we know that the first set over here under the x squared are the coefficients in front of our x's. So it's going to be x and then the diagonal of plus 2 and x minus 3. But we still have the x in front here and a 0 equals 0. So we've now completely factored it. We only have linear terms left. We can't go any further with factoring. So what we're going to do now is use this factored method to figure out the values of x that make it 0. Well, remember from quadratics, we used what was called the zero product property. Well, the zero product property works for polynomials as well, because quadratics are polynomials. If you have the product of several factors, here I have 1 factor, here 2 factors, 3 factors. I have 3 factors. The product of 3 factors equaling 0 means that one of those factors has to equal 0. So what we can do is we can go through each factor one at a time and ask ourselves, what makes it 0? What makes x equal 0? Well, x equaling 0. So there's our first solution. What makes x plus 2 equal to 0? Well, subtract 2 from both sides, and that's x equals negative 2. So an x of negative 2 would make this middle factor 0. You can see that because if you plug negative 2 in for x, negative 2 plus 2 would make this middle factor 0. And lastly, we have our x minus 3. What makes that equal 0? I'm going to add 3 to both sides, and I get x is equal to 3. So the value of 3 makes this last factor 0. So these are the 3 pieces that make each factor 0. So we would say that the zeros of our polynomial are x equals 0, x equals negative 2, x equals 3. Because these are the values of x that make our equation equal to 0. So to find the zeros of a polynomial, you need to factor the polynomial and use that zero product property. Look at what makes each of the factors separately equal to 0, because that will make the full product of all the factors equal to 0. So we do want to move on now to some other theorems and definitions that help guide us a little bit more in this process of solving polynomials or finding the zeros of a polynomial. Okay. And the first thing that we're going to talk about is this reality called the fundamental theorem of algebra. Fundamental theorem of algebra says this: if p of x is a polynomial of degree n greater than or equal to 1, okay, then p of x equals 0 has exactly n roots, including multiple and complex roots. Okay. So a couple new words in here that we have to define. Okay. The degree of a polynomial is the value of the largest exponent. So whatever term in your polynomial has the largest exponent, the value of that exponent is the degree of the polynomial. And also, roots and zeros are essentially the same thing. It's just that in one situation you're superimposing the equation equaling 0, and in the other equation it already equals 0. But for all intents and purposes, they're pretty much the same thing. So roots and zeros mean the same thing. What values of x make your equation equal to 0? So in our example, let's look at this and apply the fundamental theorem of algebra. Again, the fundamental theorem of algebra says that if your polynomial has degree n, that's exactly how many roots you have, how many zeros you have. That's how many values of x make your equation equal to 0. So, looking at our example down here, I'm finding that the first term is the term that has the largest exponent value. That's x to the third. So we would say that this polynomial has a degree of n equals 3. Degree of n equals 3. Now because it has a degree of n equals 3, we know that this polynomial will have 3 roots, or zeros. It'll have 3 values of x that make our equation equal to 0 as it's set up right here. So let's test that. Let's see if that actually works out in this situation. We've got 0 equals x to the third plus 2x squared plus 4x plus 8. So we want to work through this and find the solutions of x that make our equation equal to 0. Well, first thing we always do when we're factoring a polynomial is determine what the greatest common factor of each term in the equation is. Well, as we look at this, unfortunately, the last term here doesn't have an x on it, so they don't have an x in common. Furthermore, the coefficient in front of the x to the third is a 1, so the greatest coefficient value I can take out is a 1, which is, for all intents and purposes, useless. So we have a situation here in which nothing is in common. There's no greatest common factor. Well, the greatest common factor is 1, which doesn't do anything for us. This is the situation in which we are going to test to see if grouping will work. We remember grouping from the lesson on factoring polynomials. It's where we group sets of polynomials together. So the way we're going to group here is we're going to look at the first two terms together and then the second two terms together. Looking at these first two terms, is there anything that the first two terms have in common? Well, I notice that coefficient-wise, a 1 and a 2, nothing I can do there. However, I have 3 multiples of x in this first term and 2 in the second term. So I can factor out 2 multiples of x. When I factor x squared out of x cubed, I'm left with x. When I factor x squared out of 2x squared, I'm just left with a plus 2. So I've factored out the greatest common factor of the first two terms. Now I'm going to factor out the greatest common factor of the second two terms. That is 4x plus 8. Now the 8 again doesn't have an x on it, so I can't factor an x out. However, I do have a 4 and an 8. The greatest common factor of 4 and 8 is 4. Okay, so I can factor out a positive 4. So I'm going to do plus 4, and that's what I'm factoring out of each term. If I factor 4 out of 4x, it leaves me with an x. If I factor a 4 out of 8, it leaves me with plus 2. So now I've grouped the second two terms together and factored out what those have in common. Okay. Grouping does work on this one, and we'll see why here, because the pieces left in the parentheses are equal to each other. They're both x plus 2. What I essentially have here is two super terms. I have x squared times x plus 2 and 4 times x plus 2. Well, what do each of those super terms have in common? They both have an x plus 2 in common. So I can bring an x plus 2 out of each of those terms. And then my second factor is simply what is left after I factor x plus 2 out of this first term. I'm left with x squared. If I factor x plus 2 out of this second super term, I'm left with a plus 4. So I end up with the two factors of x plus 2 times x squared plus 4. So I've now factored my polynomial. You'll notice here I have an x squared plus 2. There's a quadratic. Unfortunately, that quadratic is not factorable any further. So we're going to have to figure out a different way to find the values that make that 0. So with our polynomial now factored, we go through each factor and ask ourselves what makes each one separately equal to 0, because if one of them equals 0, the product of all of them will also equal 0. So I'm going to look at x plus 2 first and ask what makes that 0. Well, subtracting 2 from both sides produces x equals negative 2. So I have x equals negative 2 as the 0 that makes the first factor of x plus 2 0, thus being one of the solutions of the equation that makes it equal to 0. Now let's look at the second one, the x squared plus 4 equaling 0. What makes that one equal 0? Well, in order to find what makes this 0, I'm first going to have to subtract 4 from both sides. That's x squared is equal to negative 4. Now the x has a square on it. To undo a square, I will use a square root. Whatever I do to one side, I do to the other. So the square root and the square undo each other. I'm left with x equals, now whenever I undo a square with a square root, the other side must get a plus and minus sign on it. So x is equal to positive and negative square root of negative 4. Now you'll notice that we have a negative under our square root. The way we deal with that is pop an I out. So x equals positive and negative. Because there's a negative under the root, I can bring the imaginary number I out of the root, get rid of the negative under the root. And last but not least, I know that the square root of 4 is 2, so this produces x equals positive and negative 2i. So So the square root of 4 is the 2, and then you have your I. So I really actually have two solutions here. I have x equals 2i and x equals negative 2i. So I have two solutions that come from here. So all the solutions together that I have are x equals negative 2, x equals 2i, and x equals negative 2i. Well, all of this was to answer the question, does the fundamental theorem of algebra work? Okay, well, at least in this example it does. It has been proven true. This example just illustrates that it works. We can see that because we had degree n equals 3, that the fundamental theorem of algebra predicted that we will have 3 roots, or zeros. And in fact, we do. In solving this out, we find that we do have 3 solutions that make this polynomial function equal to 0.